Greetings and welcome back. Today what we'll be looking at in this video is how to name alkynes. We'll give a little bit of an introduction into them, but mostly we'll just be talking about how we name them. So alkynes, if you recall, are molecules that have a C triple bond C somewhere within the molecule. So briefly, alkynes look like this. They are that C triple bond C, but in three-dimensional space. Really what they are is a sigma bond and two pi bonds. So we have a sigma bond where the electrons overlap between sp orbitals in between. Then we have a pi bond with overlapping parallel p orbitals up and down. And then, from your point of view coming out at you, we would have a p orbital that's doing this, and then the other half would be going away from you. So these guys are composed of those three bonds: a sigma, which has its electrons in the middle, a pi, which has its electrons above and below, and another pi, which has its electrons coming out and going back. More or less, these things kind of overlap, so instead of just thinking of it as being in between up and down or out and back, it's really kind of just a huge smear of electron cloud. So these guys share a whole bunch of electrons, both directly in between and off to the sides a little bit. Compared to a single bond, which is about 1.5 angstroms long, these are significantly shorter. They're about 1.33 angstroms long. Basically all that means is that these bonds are much shorter than a carbon-carbon single bond. The reason for that, of course, is that they're sharing more electrons. You're going to pull those nuclei closer together, and so they're going to be relatively strong compared to a carbon-carbon single bond. The reactivity, which we'll get into a little bit later, though, is still based on the fact that they have pi bonds, exactly like alkenes. Alkenes react by sharing those loosely held pi bonds. Alkynes react in the exact same way. So the reactions of these alkynes are very, very similar to the reactions of alkenes. Likewise, the naming of these is very similar to that of alkenes. One of the advantages of naming alkynes, though, comes from the fact that their geometry, if you recall, is linear. Those carbons are both 180 degree bond angles, so we have 180 degrees here, and also 180 degrees here. Therefore, these bonds are going to be completely linear. This may not seem like a big deal in terms of the geometry, but with naming, there is no difference between E and Z because nothing's on the same side. They're all completely straight. So the naming of these is actually going to be much more simple than that of alkenes. If you recall, when we named alkenes, we converted the alkane name into an alkene name by dropping the ane at the end and replacing it with ene. With alkynes, it's something very similar. We're going to replace that ane at the end, so for instance of butane, and we replace it with yne for the alkyne, so butane would become butyne. And we number it. That is essentially all there is to naming alkenes, but I will show you some examples. Let's start with I'll put a triple bond in there and onwards. So first off, when we're counting these carbons, I do want you to recall that because these are going to be linear, that would be a carbon. The junction between a single and a triple bond would be a carbon. Likewise, the junction between a single and a triple bond, there will be a carbon, and this will be a carbon as well. So, and the reason that we draw it that way is not to be confusing, but to be accurate. These are going to be linear. Therefore, not only is the triple bond linear, but the bonds coming off of that in either direction will be linear as well. So we would want to number from the side closest to the alkyne. So this would be 1, 2, 3, 4, 5, 6, 7, 9. Therefore, this would have been nonane, but instead of nonane, it's nonine because it's an alkyne. And the triple bond appears first at carbon number 3. So this would be 3-No-9, or as we could do with alkenes, we can say none 3-ine. And both of those are perfectly correct. As I mentioned on the last slide, we don't have any E or Z or cis or trans or anything like that to worry about, so that's the only way you can possibly draw none 3-ine. Once again, the alkyne is going to be a higher priority functional group than any of the other little substituents that we've talked about. So if you had a molecule like this, and I'll put a couple fluorines at the end. Even though you have a number of substituents over on this side, we would want to start naming closest to the highest priority functional group, which is an alkyne at this point, compared to all of those substituents. So this would be a 1, 2, 3, 4, 5. Alright, and therefore the name of this guy would be 5,5-difluoro 1-pentyne. Or, of course, you could say pent-1-ine in there. Alright, so what if we have both an alkene and an alkyne in the chain? If you have both of those, the highest priority functional group is an alkene over an alkyne. So for priority, at this point it is alkene over alkyne over, at this point, everything else. There will, of course, be functional groups that are higher in priority, but at this point all the other ones that we've done would be grouped together below that. Because the alkene is higher priority than the alkyne, we would want to number from the carbon closest to the highest priority functional group, which is in this case the alkene. Therefore the numbering would start over here. When you are naming something with both an alkene and an alkyne, it becomes an alkenine. Therefore, the full name of this molecule would be a 4-methyl hept 1-ene 5-ine. So notice that it's an alkene-ine. And we can't put the 1 and the 5 in front of hept because we need to put those numbers with the specific group that they're applying to. So 1 describes the alkene and 5 describes the alkyne. There is one common name for an alkyne that I want you to worry about, which is the simplest possible alkyne. This guy right here with the 2 carbons. The IUPAC name of that would be ethyne, but the common name, and in this case it's much more common, is acetylene. You may or may not have heard of acetylene before. Acetylene torches is something that's used in welding. Acetylene burns, just burns with oxygen, so it's just a combustion starting material. So you can put that guy in with O2, and just like any combustion reaction, you'll get carbon dioxides plus water. And in this case, the stoichiometry would be that. Oh, that's not right. Well, we could balance this. It would have to be 2.5 oxygens for every 1 acetylene. That looks correct. But the point is, you don't ever have to count up how much oxygen you're burning with. You just have a torch with acetylene, you light it, and the great thing about this reaction is that it burns at about 2,800 degrees Celsius. Which is very hot, which is why it can be used in metal, or in welding metal. But that is one where you need to know the common name, and acetylene is a very, very common molecule. It's one of the most common organic molecules regardless of functional groups. All right, so that is it for Advanced Nomenclature 1. I will talk to you soon.